Hello and welcome to part 3 on the series of electric circuits. Part 2 focused on resistance, some calculations, but particularly also focusing on the differences between a series and a parallel connection. So I hope you learned a lot from part 2, and part 3 will be focusing on internal resistance. Internal resistance. So what is this concept? It is the resistance of the battery. Up until this point, you have considered that the resistance of a battery as negligible, as if there was no resistance. Just to simplify things, just to get the ball moving, or ball rolling during your initial understanding of electric circuits. But now we need to start having a look at the reality of internal resistance offered by a battery, and it forms part of the total resistance of the circuit actually. So the total resistance of a circuit is not just the external resistance that we find in the circuit, but also including the internal resistance, which is represented by the small r here. Now, EMF is also a very important concept when it comes to internal resistance, and we did touch on it in part 1 of the series. EMF is the total potential difference of the circuit offered by the battery, or it can also be seen as the total energy that has been supplied per coulomb of charge. Now, since the battery has some resistance, it requires some of the voltage to drive current through it. So that means some of the voltage is actually going to be used up in the battery, and not all the potential difference is part of the external circuit, as some of it is required for the battery, like I said. And sometimes this is referred to as lost volts, because it is not being used in the external circuit, which is actually the purpose of setting up a circuit, isn't it? Because we want to make use of some appliance. Right, here's a very important formula for EMF. And EMF can be calculated by adding the internal and external voltages together. We'll discuss this a little bit in more depth now. So what we see here is a typical way of illustrating internal resistance in a circuit diagram. We have this symbol here representing EMF, and sometimes I will give you the value of the EMF. We have the symbol here for internal resistance, and they will sometimes give you those values too. Okay, and there is our external resistance. That is just the symbol for a rheostat, a variable resistor. So EMF is the total potential difference of the circuit offered by the battery, as mentioned, and total energy is supplied per coulomb of charge. So that is how we basically can work out EMF using the concept of energy and charge. More importantly, for our purposes in calculation, EMF is the sum of internal and external voltage. So we get this formula over here, as we looked at in the previous slides. And important to note here that if voltage is equal to current times resistance, then we can work out that internal resistance is included here, because internal voltage includes internal resistance, and that breaks it down to this point over here: current times internal resistance, current times external resistance. So what do these things symbolize? They symbolize the external resistance of the circuit, the internal resistance of the battery, and the total current. And that is also another way of representing EMF. So depending on your scenario, depending on what is asked, what the unknowns are, you could use any one of these different formulas depending on the specific scenario, as we'll have a look at a little bit later in the video. So there we have a voltmeter, and it takes a reading. the readings are different depending on the switch. If there's an open switch, in other words the circuit's broken, the reading on this voltmeter will be EMF, which is quite handy. If it's closed, that means there is a current flowing, and there will be a different reading here, and the reading on here will be the external voltage, sometimes known as the V load, the load of the external circuit. So one and the same thing, it's just a different name for the same thing. Let's have a look at a question involving internal resistance. Calculate the internal resistance of the cell which has an EMF of 12 volts if the reading on the voltmeter is 10 volts when it supplies a current of 6 amps. So that's interesting. They tell us the EMF is 12 volts, but what is this reading over here? It says 10 volts when it supplies a current. In other words, when there's a current flowing, when the switch is closed. That is the reading on this voltmeter. Like we saw in the previous slide, this is very important information because these are two different things, and we'll see how we use it in our solution. So since EMF equals internal and the sum of internal and external voltage, our unknown here is the internal resistance. That's what we want to work out. We want to work out small r over here. So we have EMF, we have external voltage when there's a current flowing, and we've got the current. So now we substitute it into our formula and we work out that our internal resistance is 0.33 ohm, 0.3 recurring ohm. It's a very small amount, and most of the time batteries supply a very small internal resistance. Shall we look at another question here? Look at this diagram. It shows 4 cells of internal resistance, 4 ohm. When the switch is closed, voltmeter V1 connected across the battery reads 10.8 volts. Okay, so that's important when it's closed. So that means it's not the EMF, it's the external voltage. That should be 0.4 by the way, not 4, 0.4. So a couple of questions here. The reading on the ammeter, the EMF of the battery is what we need to calculate, and then thirdly, the switch when it's opened, is the current through the ammeter greater than, less than, or the same as before? We need to give an explanation. And the fourth question is calculate the reading of the voltmeter with the switch open. Alright, so let's have a look at the first question, which is calculating the reading on the ammeter over there. That would be the total current. How do we do that? Well, we can work out the total resistance externally, which is the resistance series plus the resistors in parallel. We're not going to go into detail how we work this out now, because we should know it's 1 over 6 plus 1 over 4, etc. But it works out to be 2,4. So it's 3 plus 2,4, and that gives us 5,4 ohm. That's the external resistance. So the current in the external circuit will be the voltage of the external circuit divided by the resistance in the internal circuit. We know that the voltage of the external circuit is 10,8. We know that the resistance is 5,4, my apologies, and then the current is 2 amps. Having a look at the next question, we calculate the EMF of the battery. So we use our formula over here. We substitute our values that we do have. We just worked out that the current is 2 amps. The internal resistance is 0,4 for each one of these cells, and there are 4 cells, 1, 2, 3, 4, and so that's 4 times 0,4 gives us 1,6. We add 1,6 to 5,4, and we multiply by 2, and we will get 14 volts. So that is our EMF value. And now looking at our next question, when we open the switch, it's been closed the whole time. If we open it here, what happens to the current that flows through the ammeter? Is it greater than, less than, or the same as before? And we need to be able to understand why that is. can't just guess. So the answer is it is less than. Why? Why is it less than? Why would the ammeter reading be less than before? Well, let's go into the explanation. When you open the switch here, it will increase the external resistance. Why? Because this was a parallel connection. When you add more resistance in parallel, you actually get a smaller resistance. But removing this resistor out of the circuit causes this to become a series connection, which will increase the total equivalent resistance, and increasing the equivalent resistance will cause a decrease in current. Remember, there's an inversely proportional relationship between current and resistance. Right, so that is the end of part 3 of this series on electric circuits. I apologize for some of the small errors, but I hope you understand this concept better and that you've learned something. Thank you for watching.